I will let your presenters take it away.
So thanks, Brett, and welcome everyone. Thanks for joining today. We're excited to give you an overview of the wildRtrax package. So a few quick notes before we get started. So we assume that in joining today that you're here for a few different reasons. So we're going to assume that you're using an environmental sensor, such as an ARU or a camera, that you know or are aware of wildTrax, which is an AVMI maintained platform for maintaining, storing, processing, sharing, and discovering environmental sensor data, which you can sign up for free for today at wildtrax.ca. And we also assume that you know R, which is a programming language mainly used for statistical computing and data analysis. And with that out of the way, and all these things combined together, we get the wildRtrax package. So it's an R package containing functions for data organization, analysis, and standardization with the wildTrax infrastructure for users who work with environmental sensors.
Right.
Why did we build it? Well, additional analytics and functionalities that have been built in parallel with wildTrax allow you, the user, to get more out of your environmental sensor data while still providing a standardized and harmonized workflow to help answer important and biological, ecological questions. So of course, as Brett mentioned, wildRtrax is supported by the Alberta Biodiversity Monitoring Institute and the folks you'll meet today. But hopefully it can be you as well. wildRtrax is an open public repository, and we encourage to support a community of contributors and collaborators to help make the package even better. And you'll learn how to contribute to the package if you're interested in a little bit. So today's presentation will be broken up into 5 parts. First, we'll quickly look at package installation and getting things started with acoustic data pre-processing. Then once you have your processed sensor data from wildTrax, we'll move into authentication and data downloading, followed by a comprehensive look at all the different functions that can help you to wrangle and analyze your sensor data together. And finally, again, we'll look at how you can contribute to the package. And so by doing this, we're avoiding the need for CSVs and getting your data downloaded so that you can move your data directly into an analytical framework that may become, easier to edit and change along time. And this is really so that we can aim towards interoperability using the power of APIs and data standardization to get the most out of your sensor data. All right, let's really quickly start with installing the package. So since wildRtrax is not a CRAN package in R, you'll instead need to use the remotes package followed by the install GitHub function. And using the repository name you see here, you'll be able to install wildRtrax to your machine. It will also prompt you to install any of the package dependencies before you begin as well. And so as we continually work on developing the package, feel free to download the development version at any time as well. So you can see just the @development addition to the string here. And this allows you to get any recent fixes and enhancements before they're released. Just be aware that this branch may be unstable at times. And so by downloading the development package, just be aware of that. All right, let's get started with some acoustic data pre-processing. So this is a series of steps and functions to help you determine what audio data you even have, as well as some of the values you can extract from that media in order to determine what you're going to use for your data processing. So again, let's load the package now that we've downloaded and installed it. And wildRtrax does also replace certain package functions with others. So check the warning messages in the console to see what's affected for you before you get started. And before we're going to use our first function, it's also best to plan how your machine is going to use and most efficiently scan and run the pre-processing functions. So here you can use the plan function from the future package in order to assign a strategy. So finally, we can get to our first function, which is WT audio scanner, which is simply just a function that scans the directories of audio data that you have and returns standard naming conventions and columns that match the wildTrax infrastructure. So for example, here, we're going to have scanned this, taken the audio scanner function and run it through an AVMI ecosystem health location, which is an ARU that's deployed usually in the winter every year and activates on a set schedule between March and when it's retrieved in the summertime. And with this, we get 1,166 recordings that were collected at this location. So given the volume of this data that's collected at each location in each year times the number of ARUs we use, we need to select which files we're actually going to process for the species data that we're interested in. So let's look at some of the variables we can use to filter by. So looking a little bit at the column names, you can see that the ones that are most critically important here are the location, which is where the recording was taken, and the recording date time, which is when the recording was taken. So this is providing that spatial temporal information to your audio data. And you can see here that this is derived directly from the file name itself that the function scans. So here we have 339 Northwest as the location name and the date time accordingly. You can also add extra arguments to the function, such as setting the extra calls to true will allow you to get sample rate, the length in seconds of the audio file, as well as the number of channels it has. And you can even assign a time zone to the recordings if you want using the TZ argument. Okay, so here, let's filter our files by a series of dates and times, for example, in order to, for example, just get the morning recordings during a breeding bird season. And here I'll even create an extra column called hour using the wildRtrax package. And by doing this filtering by just a few dates and times, I can filter my list of recordings down to just 22 files. So here's a really simple example of how you can scan your data and then filter out by a series of criteria that you're interested in. So next up are two functions which derive the output from the QUT Ecoacoustics Analysis Program. AP, for short, is a software package that can perform a different suite of analyses on audio recordings. And so here, wildRtrax takes the summary from the spectral and summary acoustic indices and produces the index functions and the long duration false color spectrograms. The first step here is to download AP onto your local machine and define its path, which you see here in the run AP function. And then from there, you can use that alongside the files that you scanned from WT Audio Scanner to run the program through RStudio itself. So when you've completed the run, the next step is to use this glean AP function. And what that's going to do is extract the output that you're interested in. Glean AP will output a list of 3 different objects. The first is a tibble of just the raw data that you've scanned. The second object here, which you just see in results, is the summary of the indices that are plotted here. So once again, we've scanned all of the audio files from that ecosystem health location from March until July. And with this acoustic complexity index here, you can clearly see when migration is taking place as acoustic complexity increases and then decreases throughout the summer as the diversity of calling species decreases as well. The third object that comes out of the glean AP function is the long duration false color spectrogram. So what you're looking at here, again, are the summary index results from the various indices that are included in the software package from all of the recordings from that location again. So this is 30 gigabytes of audio data that's actually condensed down into a single image. And so you can see here the months that I've labeled below, where you can have migration taking place at the end of April, beginning of May, and then decreasing throughout the summer, which you can then manipulate further if you're looking to only get certain results that you're wanting to filter from these files. So here I'm just taking the files and I'm filtering between hours of 9 p.m. and 3 a.m., which produces a shorter LDFC, but still you can see some pretty interesting patterns. And so given that these are indexes and not spectral signatures, you need to interpret them a bit differently. But for example, what you're seeing in most of the green color here are Swainson's and hermit thrushes that are vocalizing in the evening hours, especially strongly in the midsummer. And so the value from filtering and generating indices from your files is that it allows you to pre-select recordings based on criteria that you define in a standard way. So that once you get to the point of generating tasks, your pipeline can be very simple, like the one I'm showing here. So here I'm joining against a lookup table, which is called the ABMI blocks. And this is simply the stratified sampling design that we use to select recordings for our ecosystem health program. This will select 12 files across the deployment of this ARU, which then I'll just copy simply to my local machine. And then I can upload directly as recordings and tasks into a project by going to WildTrax, selecting a project, and then selecting manage and upload recordings to project. Similarly, if I'm not quite ready to make tasks yet, I can use the WT make ARU tasks function to take those filters that I've used to select the files that I'm interested in, and then generate tasks later, but still be able to upload recordings through the organization. So alternative, but sometimes you've already got tags, say from a classifier output, no problem. WildTrax has got a couple functions that can help you out there. The WT song scope tags and WT kaleidoscope tags functions easily convert the classifier outputs from these different programs into tags, which then you can use manage upload tags to sync your data later. Just remember to make sure you upload your recordings into WildTrax first, and then the system can join both the recordings and the tag outputs that you get from these classifiers together in a project. There are a couple pre-processing functions available, but maybe we'll look at these another day. And with that, I'm going to hand it over to Marcus.
Thanks, Alex. I'm going to request control of the screen here. Let's see how it goes. Okay, I'm in. All right. So yeah, I'm going to take us to the next phase, which is sort of, Alex talked a lot about the pre-processing side, especially on the acoustic data. But of course, we can all use the WildTrax platform to do our tagging, whether that be the acoustic recordings or the camera trap images. We do all the tagging, and then the magic happens again after that once we want to import that data into R for analysis. So wildRtrax makes that really seamless, hopefully, and quick to do. So you can actually authenticate into WildTrax directly in the R console. And the way you do this is that first you need to set up your username and password to WildTrax as what are called environment variables. And just a quick note that they do need to be called these two values, WT underscore username and WT underscore password respectively, because that's what the later functions will look for. So here I just have a guest account, but of course you substitute your username and password in a line like this. And I just do want to tell everyone that to be careful, because these values, this is a sensitive piece of information, and if you include that in a script that you might publicize anywhere, that means someone could access your WildTrax account. So there are, several ways you could deal with this. One solution is just to save a local R script with those values and that you call at the beginning of any other script, like this. Or another solution I've used before is the keyring R package, which allows you to securely store those credentials locally without actually ever having them typed out anywhere, which is really nice. Anyway, a couple options. But once you've done that, there's a function in wildRtrax called WT underscore auth. All you have to do is run that, and you will be authenticated into WildTrax. So what happens beneath the hood is that the package will create what's called a hidden environment. And then WT auth will retrieve an auth0 token, which is basically the way that WildTrax accepts login information. And that will be stored in your R environment. And so if you ever want to check it out, what those values actually are, you can take a look. Like, for example, when I rendered this slide deck, the auth0 expiry time, so you have about 8 hours to use the same token, it will tell you the expiry time. So that's kind of how it works underneath the hood. You don't really need to know too much about that. The beauty, though, is that you can now use that token to interact with your WildTrax data directly in R. So the functions in wildRtrax will take that token and will supply it to the WildTrax API, and you can download information directly. So here we have a function called WT underscore get download summary. All you have to do is supply the sensor that you're interested in, whether that be ARU or CAM or point count, and you'll get back a nice tidy data frame of all the different projects that you have access to. So one of the magic, I think, comes from the download report function, which actually mimics exactly the data download page on the WildTrax website. So hopefully a lot of you who have used WildTrax before have gone through the process of downloading your data, your tags. So you have to click through various things and download a CSV. But thankfully, the download report function in wildRtrax makes this super easy. All you need to supply is the project ID value, which you can get from that previous function I talked about, get download summary. So here I'm just using the example of the ABMI's Ecosystem Health Camera project from 2014. You obtain this project ID value, which is in this case just 205, which is obviously meaningless to us, but it's just the way that the database organizes the projects. And then in the download report function, you supply that 205 ID, the sensor, which is cam, and then the report type that you want. And then you'll get back a nice tidy data frame, which is awesome. So basically this kind of supersedes the process of downloading the CSV, storing it in a folder somewhere, reading that CSV into R. This kind of makes it easy to just have that entire process scripted. So quickly, you can do 2 projects at once, right? That you can iterate over a couple different projects. This makes it really easy to script. To avoid a for loop, I use the per package and the map_df function. And you can just package a bunch of projects together into one data frame very quickly and nicely. So there are a bunch of different available report types. So they're kind of listed here. There's a main report for both the camera and ARU sensors, which basically is supposed to, the idea is that it contains the vast majority of information most analysts would want. But then there are other supplemental information here if you're just interested in the images, the tags themselves, the locations, that kind of thing. So I won't run through them all, but you can look at the definitions and all the information available in each of those on the WildTrax guide. And so I guess, yeah, we come to the question of sort of, so what? You know, you've made a slightly slicker version of read.csv, which we've all used, you know, big deal. I think my counter to that would be that there's a lot of benefits to scripting. One of the biggest ones for me is actually always getting the most up-to-date version of the data, because you know, oftentimes data will be tagged, but then, you know, if you have collaborators, someone else might go in there and do a little bit of extra tagging, or maybe there's some changes to the species verification that's happened. So you kind of always just want to be pulling the most up-to-date version, so you don't have to worry about versioning your data. You know, your collaborators, if they have access to the project, they're working off the same data that you are. Reproducibility, of course, and you know, you just don't have to store all these CSVs on your machine, which is great. Okay, so I'll briefly just talk a little bit about a few camera analysis functions that we have in wildRtrax. So we have the tag data loaded, but of course we want to transform it into something that's more useful for something down the road, like modeling. One common task that a lot of people like to do as a first step is to evaluate the independent detections in their camera data. So kind of group the detections into independent events. So we have a function wildRtrax for that. It's called wt_ind_detect. And so it's designed to work with the output from the download report function. And it allows the user to specify a detection threshold, so minutes or hours, that kind of thing. So we'll use the example of the ecosystem health data again. You supply it to what you just downloaded, so the raw data. You specify the threshold and the units. So in this case, I said 30 minutes apart. So all the detections that are 30 minutes apart, I want to group together. And then a few convenience arguments here just to remove humans and like domestic animals and things like that. And it gives you a nice tidy data frame of all the detections in your data, which you can then plot, you can visualize, you can feed into different analysis, modeling, that kind of thing. In this case, there were 313 independent detections in this data. So one more, the last one that I'll talk about is a function that'll actually put a lot of your camera data into a nice format for certain modeling downstream, so like habitat modeling or occupancy. And often we want to basically take that detection data and we want to spread it into or summarize it into the number of detections over specified time intervals. And we also want to include zeros, right? So the star of the show that I like to say is WT_summarize_cam. You specify these arguments. So you're putting in your raw data, you're putting in that detection data, the time interval that you're interested in. So that's, monthly, weekly, daily, that kind of thing. The variable that you're interested in, sort of the number of detections or whether or not a species was detected, so presence, absence. And then there's two desired output formats that are available, either wide or long. And so lots of analysts on the call, I'm sure, will be familiar with the pros and cons of both those two. This is what it looks like. You supply your detection data, you supply the raw image data, the time interval you're interested in, the variable you're interested in, and your output format. And then you'll get a nice tidy data frame of what that looks like for your data. So and it's kind of hard to see here, but so this is the week of the year, so the 13th week of the year, the number of days of effort, which is 7, it should be 7 per week. And then for each species, you get whether or not it was, or how many detections in this case. So lots of zeros and then a few ones. So yeah, that's kind of I think a nice jumping off point for future modeling, and hopefully can get you started with your camera data. And so one last slide, I just like to show this off, is that hopefully wildRtrax can help really make your analyses very streamlined. So you can see here, I got all the way from when I started talking to the end here in just about 10 lines of code. And hopefully that kind of helps you get on your way and start straight into the science without having to do as much of the upfront work of the data wrangling. So I'll pass it off to Ellie.
Thanks, Marcus. So just bear with me today. I'm a little froggy in the voice, but I'll try and speak clearly. So we're going to look at some similar functions on the ARU side. Just waiting for control. There we go. So we're going to look at some similar functions on the ARU sensor side. We're going to do some wrangling with acoustic data and then a couple functions that'll get us into analytics. So we'll do 2 parts. First, we're going to look at 3 different functions for data wrangling that will help you kickstart your analysis. We'll be reviewing the functions in this order, but they can also be used independent of each other. And then we're going to look at a couple data analytics models that'll get you straight to your statistical model. So you have some processed acoustic data. You use the functions that Alex presented. You got your tasks into WildTrax, and you went through and you processed that data. So we're going to look at pulling down that data and wrangling it for analysis. So just a quick recap, because the data download really is a pretty key function. So we'll authenticate, we'll look at the projects we can access. We're going to do a quick sidebar here, public service announcement. There is a lot of public acoustic data available in WildTrax. So if we look at just the published public projects and the ones with the report, there are 87 different projects that you can access at any time in WildTrax. And those 87 projects represent almost 750,000 tasks. So that's like different recordings that have been processed in WildTrax. Okay, we're done our PSA. Let's go get some data. We'll pick something small just to play with here. And what did we get? We got a public project from Elk Island National Park to play with. So we'll go and we'll download that with the download report function, and make sure you're specifying the main report here. So all the functions that we're going to look at today operate on that main report. That's the one that Marcus talked about, that should provide, pretty much all the basics you'll need as an analyst to do some basic or even some advanced analytics with your ARU data. So what does this report look like? It's a long object. So each row for the area sensor is a tag. So that's that box around an individual bird or a group of birds. And these are all the different fields of data that you get in that object. Okay, so let's start thinking about some data wrangling. First, do we need to do any filtering? Well, if we look at the species that we have in this object, we've got some birds, we've got yellow warbler, we've got Baltimore Oriole, but then we have light traffic, and we have light background noise, and we have a red squirrel. And maybe we don't want to do an analysis on light background noise. We're just interested in birds. So we can use the tidy species function to remove species groups that you aren't interested in, or groups of sounds. So you can remove some or all of the following groups. You can remove the mammals, the amphibians, the abiotic noise. So that would be like that light background noise that we just looked at. You can remove the insects. You could remove the birds, but I would argue, why would you want to take them out? And you can also remove your unknowns. So if a listener couldn't quite get to species, sometimes things are labeled as unidentified passerine or unidentified sparrow. You can take those out. Okay, so let's do that with our data set. So we'll use that function. We're going to use zero fill equals true, just to make sure that we're keeping surveys with no birds detected. Okay, so let's check our species list again. Looks great. Onward. Okay, so, continuing down, exploring our data, let's look at our distribution of counts. We try and plot a histogram, and we're going to get this error. It says X must be numeric. Uh-oh. Well, why would count be a character value when we're expecting an integer here? Okay, well, if we look at our count values, we've got this TMTT character. There's value in here, and there's 42 of them in this data set. What is a TMTT? The TMTT stands for too many to tag, and in the guide, it's defined as an abbreviation used to indicate an uncountable number of individuals within the bounds of a tag. Basically, this is what a listener uses when there are just too many individuals in a particular task to try and separate them out. And so they'll often draw a box around a group of them and label it as TMTT. I will note the listeners are phasing out the use of TMTT. So this function primarily is applicable to historic data sets, but it is a good one to be aware of. Okay, so we have these TMTTs. Well, what are our options? We could convert our data to presence absence, so ones and zeros, but maybe you're interested in abundance. Maybe you don't want to do that. You could use regular expressions to get abundance estimates out of the comments field. We don't recommend this. A, it's a lot of work. B, it's inconsistent across the comments field. It's not always there. Or you can use the replace TMTT function. So we've gone and we've regex those abundance estimates out of the comments field for you. And we've created a model that predicts abundance for TMTT values based on the intersection of the species and the observer of the tag. Okay, so let's go replace our TMTTs. And so what does our distribution of counts look like now? Okay, well, that's great. We've got integers now, but this distribution looks kind of funny. Well, recall that each row is a tag. And so to actually get to abundance for each species in each task, we need to use the make wide function. So make wide aggregates the counts by task and species and provides a column of counts for each species. So each row becomes a task, and then you've got the metadata at the front of the object, and then you've got a column for each species with count in each column. And so we can do that. We can filter by sound type when we do this. So, maybe we only want counts of song detections, or, maybe we want call, or, maybe we want all of it. So let's keep everything in our example here. And so now what does that output look like? So you can see here, we've got the columns at the top that describe the task, like longitude and latitude, what the recording ID is. And then we start to see these columns here for each species. So all their flycatcher, American bittern, et cetera. Okay, so now what does our distribution of counts look like? Let's look at white-throated sparrow, and it looks really, really lovely. Data wrangled, check. Okay, so now we'll move into data analytics. I should mention the analytics area is under active development. We have 2 tools so far, but there's probably a lot more coming down the pipeline. Spoiler alert, this is a great area for contribution. Marcus is going to tell you how to do that at the end. So the 2 tools that we have so far are format occupancy, which formats data for single species, single season occupancy models in the unmarked package. We get a lot of questions about this one, so we thought we would make a function for it. And then the second was the QPAD offsets function, which calculates QPAD offsets to account for imperfect detection. And I'll explain a little bit more about what that is when we get to it. So format occupancy functions on the long form of the data. Don't use make wide before you use format occupancy, but it'll work on the output of any of the other functions. When you're using this function, your site covariates must be user supplied. So we can make some up. It should just be a data frame with one row for each location surveyed. You can see the help file for the unmarked frame occu function, which is what this is a wrapper around if you want more details. And just when you're making those site covariates, make sure that you sort them by location so that the order matches the other objects that we're going to create with the format occupancy function so that you can match your site covariates to the sites where your surveys are. Okay, so what do these site covariates look like now that we've made up some values for tree cover, we'll call it. It's really just random numbers. So yeah, it's just a data frame, 2 columns, a location, and the covariate that we made up. Okay, so now let's use their function. We use the format occupancy function. We're using the output of the replace T and TT function here, but again, you could use the output of any of the other functions other than make wide. We're going to format for white-throated sparrow, and we're going to throw that site covariate object in there. So let's look, what does this give us for observation covariates? What's built into the function already? We've got day of year as well as the square of it, hour of day, and the square of it. We've got methods. So whether your task was tagged with 1 species per tag or 1 species per minute, and then we've got observer. Again, a great area via collaboration if there are other observation covariates that you'd like to see as part of the format occupancy function. Okay, so let's run a model. Let's test if detectability varies between observers and whether occupancy varies by our made up site covariate tree. So there's our function, and what do we get? Well, we're not seeing a lot of differences between our observers. That's great, good job, observers. And we're not seeing any relationship between occupancy and tree, which is a relief because we made it up. Okay, so our last function we're going to talk about is the QPAD offsets function. So QPAD is a statistical approach for dealing with imperfect and variable detectability. This is an approach that was put together by the Boreal Avian Modeling Project. Here's the citation for the original analytical methods. And I should mention that both ABMI and the Boreal Avian Modeling Project use QPAD in our species distribution models. How does it work? Well, what QPAD does is it models availability for detection, or phi, with removal models, and perceptibility, or tau, which is basically how far you can hear a species, with distance models. And then the two are combined to provide values that can be used as statistical offsets in a wide variety of models. Okay, fine, that's useful, but how do you get the offsets? Well, we at BAM have actually already modeled phi and tau for you under a variety of conditions with a variety of covariates. And so the QPAD offsets function uses those models that we've already put together to calculate custom offsets for your data set. So we just throw our wide data object in that QPAD offsets function. We can make offsets for all the species in it, or we can just pick a subset if we're only interested in a few. So here we've just picked ovenbird, white-throated sparrow, and yellow warbler. And then if you want to put it in a model, you can put it in a linear model, you can put it in a mixed effects model, you can put it in a boosted regression tree, you can put it in a Bayesian model. In a linear model, you're just using this offset equals argument in addition to your regular model formula and your data argument. And so that's the end. I'm going to pass it back over to Marcus. Thanks for listening.
Okay, I'm just going to wrap up by just briefly one slide on how you all can contribute to wildRtrax if that's something you're interested in. So the first is just sort of the standard. There's a package GitHub repository which we can link to. And so if you think you found a bug, or like a function is not working a certain way that you think it should, or you would like to suggest a new function or feature, please use the issues tab on the repository, the GitHub repository. We'll do our best to respond in a timely manner, and that's a really valuable way to kind of communicate to the community what the state of things is and if you found any bugs. And then The next is pull requests. And so I want to emphasize that we really welcome this at any time. So this is a way to contribute to the package. If you have let's say a function that you've developed for an analysis that you're doing or have done, or just something you think would be really cool and be used by the community, we would love it if you would contribute. So I can show you how to do that. And I just want to say that you will be acknowledged as a package author too. So it's a good way to kind of, test your chops and get out there and try to develop a new skill. And we really want to make this as inclusive as possible so that it's driven by the community and not just us three in our offices thinking about what might be cool for people. So I do really want to emphasize that we will be happy to work with you to do that. So I'm just going to share my screen here quickly and show folks how a simple way to do that. I hope you all can see it. Getting a head nod from Ellie. Okay, so this is the GitHub repository for the wildRtrax package. Hopefully lots of you have seen this already. You can just read a little bit about all the functions. So what you would do if you wanted to submit a pull request, the first thing you do is that you would fork the repository. So what this does is basically it creates a whole copy of the repository, the entire package and all the files associated with it. And it creates a copy for yourself to do whatever you want with. So rather than choosing AB biodiversity here, I would just have it under my own private profile. And I would create the fork. Give it a second. Hopefully it takes not that long. Okay, so I actually now have an entire copy of wildRtrax on my personal GitHub page. And so that means I can actually go in and do anything I want with it, including cloning it. So I could clone this and interact with the files in RStudio and then push and pull to this specific repository. Or I can even just make small changes here just right on GitHub. And so that's what I'm going to do actually, is I'm going to open up the README. I'm going to say, I think that maybe this could be explained a little bit better. Maybe I have a typo I want to help fix, anything like that. I would say open data science is awesome. Right? That's just something I think the README should say that, and I would like to suggest that. So I'll make the changes to this README. I'll commit the changes. Here is my suggestion, and I'll commit the changes. So that change has been saved now to my local wildRtrax repository on my own page. But if I go to the page now, it'll tell me that this branch is actually one commit ahead of its parent, its main, the AB biodiversity wildRtrax repo. So what I would do, if I think that this is a good change, I really think that it should be a part of the main repo. I would say contribute, open pull request. You can update what you want to say about it. This is why I think this should be added. Oh my God, I'm butchering this. But and one thing I want to emphasize here too, it would be best for just for us and our workflow, if you would, instead of contributing the pull request to main, just under this dropdown, go into the development. So that way we can play around, we can test the function or changes that you make before merging it into sort of the official version of the package. So basically I want to pull that change into the development version of the main package. Title, hit create pull request. And that should be all you need to do. And so if we go back to the main page of wildRtrax at the AB Biodiversity organization, you see on this tab up here, there's a pull request, and then Alex, Ellie, or myself can go in. We can take a look at what it is. We'll see your comments. We'll see anything that is creating any confusions, and we can choose to merge it if we'd like to. And so we can work with you guys, we can go back and forth. If there's code that you want to change, or if you want to update anything or find a bug, we can go back and forth. And this is a really nice, elegant way to contribute to open source software. So I know that was a lot. Hopefully this will be recorded and you can go back and take a look at those steps. But I did want to emphasize that we really do value and would love if people would contribute, because we don't have all the ideas. We're not necessarily even expert software developers. So if folks have ideas and want to contribute, we totally welcome them. Okay, off my soapbox.
Okay, well, thanks guys so much. I'm just going to stop the recording here.